All right, geometry students, here we go into section 6.2. And 6.1 was kind of an umbrella section, kind of covering all polygons in general. But now we get into 6.2, which is more of a preview of what we're going to be doing in the rest of the chapter. And the number one thing we're going to be dealing with for the rest of chapter 6 is quadrilaterals. And if you recall your definition from section 6.1, a quadrilateral is just a blanket generic name for a four-sided polygon. So to be clear, every four-sided polygon is a quadrilateral. That's its definition. But now in 6.2, we start dealing with one specific type of quadrilateral, and that is a parallelogram. So 6.2 deals exclusively with that. So we'll start off with a definition of it right here, everybody. A parallelogram is defined as a quadrilateral with two pairs of parallel sides. Now, let's not go too fast through this. The first thing it says in this definition, a parallelogram is a quadrilateral, which means that it's a four-sided polygon. And one thing we'll talk about during the course of this chapter, definitions build on each other. They build on existing definitions. So the fact that it says right away here that a parallelogram is a quadrilateral already tells us that this is a four-sided polygon, meaning that it's a closed figure made up of four line segments. We know that already. But now going further, what makes a parallelogram unique or special among all quadrilaterals is the fact that it has two pairs of parallel sides. So obviously, adjacent sides can't be parallel to each other because they intersect. So it's got to then be the opposite sides of this figure that are parallel to each other. So we could use an arrow here to show that line segment, oh, that was ugly, AB is parallel to DC. In fact, I'll go ahead and write that right here. Line segment AB is parallel to line segment DC. And then this side on the left, AD, would have to be parallel to the side on the right, that being BC. So AD would be parallel then to BC. So that's what we know in a parallelogram, that the opposite sides of the figure have to be parallel to each other. This right here, everybody, is the notation that we use when we're talking about a parallelogram. You guys got used to the triangle symbol, triangle XYZ, which we used a lot within the first semester because we spent so much time talking about triangles. Well, now in chapter 6, we use that symbol right there, everybody, which, brilliantly, is a small parallelogram. We use that to denote parallelogram. All right, I didn't draw it very well, but it's supposed to actually look like a parallelogram. So, in naming any polygon, you can start, this is the same rule actually that we used for triangles, in naming any polygon, you can start from any vertex that you want. You can see right here that I chose to start at vertex A. And then from there, you can go in either direction you want, either clockwise or counterclockwise. However, you have to keep going in the same direction. So I started here with A, and then I decided to go clockwise, and that's why I named this figure parallelogram A, B, C, D. But I could have also called it parallelogram A, and I could have gone the other direction now, D, C, B. That would have worked. I could have started at another spot. I could have named this parallelogram, how about B, C, D, A. That would have worked. Okay, so there's actually, let's see guys, 4 different places you could start, A, B, C, or D, and 2 different directions you could go from any one of those starting points. So there's actually 8 different and all equally correct ways of naming this figure. The one thing you're not allowed to do, everybody, is to start at a vertex, like let's just say start at C, and then jump across the figure to A. C and A are not adjacent vertices, they're opposite. So however I wanted to finish this, C, A, D, B, that right there is an invalid way of naming this parallelogram because I jumped across the figure using a diagonal from C to A. So you can't do it that way. But again, there's 8 different ways to name this particular figure. You can start from any vertex you want, and you can go in 2 different directions. All right, so what we have right here, guys, is the definition. In fact, you might even want to write that down. That is the definition of a parallelogram, a quadrilateral with two pairs of parallel sides. Now, I bring that up because as you look at this figure, which I'm pretty sure I used the smartboard tool to draw, it looks way too pretty for me to have drawn that by hand. There are other things that you might have noticed about that figure that are not part of the definition of parallelogram, but they are properties of parallelograms. So these are things that mathematicians just kind of noticed after the fact tended to happen when they drew themselves a parallelogram. Now let's see, do I have a parallelogram tool here on this? I do. How about that? So I'm going to draw another one right here in this figure, guys, and we'll Okay, so if we have a parallelogram here, something that looks maybe like that, there's a couple of other things we might notice going along with this. All right, the first thing, guys, theorem 6.3. All right, now notice, these are theorems that are built off of an existing definition. And theorem 6.3 says that opposite sides, and I should have written in a parallelogram, but I thought we would shorthand this just a little bit. It also says above that we're talking about parallelograms here. Opposite sides in a parallelogram are, and when I ask people in class, what do you guys notice about the opposite sides, two things come up. Number one, they're parallel, but number two, they happen to be congruent as well, or at least look congruent. Well, don't write this down, guys. It is true that opposite sides in a parallelogram are parallel, but we don't need to write that because we already knew it from the definition of the parallelogram that we wrote down before. So the fact that we knew this figure was a parallelogram told us already that the opposite sides were parallel. But this theorem right here tells us something different now, that the opposite sides in a parallelogram are congruent. Now, I don't know that it's been made abundantly clear to you guys why we spent so much time back in chapter 4 proving triangles congruent to each other, but this is kind of the reason why we did that. You don't need to write any of this down, guys, and it is not going to show up on a quiz or a test, but if I were to draw one diagonal within that figure here, well, let's think about what we know. We know for a fact that because this is a parallelogram, the top and the bottom sides are parallel. That means that this angle is congruent to this angle because those are alternate interior angles between parallel lines. Now, likewise, the left side is parallel to the right side. That means, everybody, that this angle here is congruent to this angle. Once again, because we have parallel lines cut by a transversal, so their alternate interior angles are congruent. What else? We know that that diagonal is congruent to itself. And if you think back to the way we looked at it in chapter 4, we now know that the two triangles within this figure are congruent by, ask yourself why, everybody, that is what angle-side angle congruence looks like. Now, if we know that those two triangles are congruent, we know that their corresponding parts have to be congruent as well. That is the reason why, it's not just an assumption, you guys, the top side is congruent to the bottom side, and the right side is congruent to the left side. That's how we know for a fact, not an assumption. That's how we prove that the opposite sides in a parallelogram are congruent. Because you can cut that parallelogram up into two triangles. You can demonstrate using the definition of a parallelogram and theorems that we've already learned this year, we can demonstrate then that those two triangles are congruent, and using a concept that we talked about, usually we talk about at the end of chapter 4, called CPCTC, corresponding parts of congruent triangles are congruent, we know then that the opposite sides in that figure have to be congruent. Okay, as fun as that was, I'm going to undo most of the markings that I put in that diagram because it's going to get difficult to show what's going on here in the rest of it. So that was theorem 6.3. Opposite sides are congruent. Let's move on into theorem 6.4. Consecutive angles are blank. All right, now for some of the same, actually, give me just a second, guys. I want to get rid of this guy too. Oh, that's not what I wanted to do. You, come here. All right. I think if I do that, hey, I can get it to go away finally. Okay, theorem 6.4, consecutive angles are blank. All right, guys, so if I name this the same way I did the last one, A and B and C and D, for consecutive angles, for example, we'd be talking about angle D right here and angle A right over here. Well, once again, we know that we've got parallel opposite sides here because of the definition of a parallelogram. If you go back to your vocabulary from early in chapter 3, when you have two parallel lines like this one and this one cut by a transversal, angles A right here and D right here are consecutive interior angles. And one of the theorems we learned early in chapter 3 said that when parallel lines are cut by a transversal, consecutive interior angles are supplementary. So that, let me undo some of these markings here, that is what we know here from theorem 6.4. Consecutive interior angles are supplementary. And I certainly hope everybody by this point knows the definition of that word, because we talked about it within the first couple of days of this year. Supplementary angles have measures that add up to 180 degrees. Okay, so we know then that angle A and angle D would have to be supplementary. How about theorem 6.5, which deals with opposite angles? Angle A right here and angle C right here. Well, building off of theorem 6.4, let's just assume for the time being, everybody, let me make that a little smaller here. Let's just assume for the time being that angle A looks like it's about 120 degrees. That would mean that angle D would have to be the supplement of that, which would be 60 degrees. But now if I go back to theorem 6.4 again, consecutive angles are supplementary. Angle D right here and angle C, well, those are consecutive angles as well. That means that C would have to be 120 degrees as well. Well, let's keep going. C and B are consecutive angles as well. They've got to be supplementary, so that means that B has to be 60 degrees. And now, as we look at opposite angles in this figure, angle D is 60 degrees, and so is angle B. What else? Angle A is 120, and so is angle C. So that certainly seems to tell us, guys, that in any parallelogram, opposite angles are going to be congruent. Okay, so that's where we're at, and I think right now I'm going to regret, oh, that's not what I wanted to do. Let's undo that. I think I'm going to regret all these markings that I put in here, but okay, well, it is what it is at this point. Theorem 6.6, last one here, guys, and this is the tricky one out of the four. The diagonals blank. Well, that's all I wrote. So let's draw in the diagonals, guys. A diagonal is a line segment that connects two non-adjacent segments within a polygon. So line segment DB is one of your diagonals, and line segment AC is your other diagonal. All right, what do we know about those, everybody? They are not, as a lot of people want to say, congruent to each other. You've always got one diagonal in a parallelogram, as long as it's a parallelogram that's not also a rectangle, you've got one diagonal that's longer than the other. If I ask you guys to think about that, this one is going to be line segment BD. Okay, the one diagonal that connects the two acute angles is always going to be longer than the one that connects the two obtuse angles. The kicker here, guys, is that the diagonals in a parallelogram are always going to bisect each other. And if you remember the word bisect, everybody, that means that this point right here creates congruent segments. Let me call that point E right there in the middle. The fact that these diagonals bisect each other means that DE is congruent to EB. And it also means that line segment AE is congruent to EC. Now, the other thing I wanted you guys to see right underneath that, guys, that means that the two diagonals have a common midpoint. Point E is the midpoint of diagonal AC, and it's also the midpoint of diagonal DB. So that's what it means for two diagonals in a parallelogram to bisect each other. They have the same midpoint. So let's put these last two slides together in context here, everybody. We learned our definition of a parallelogram, opposite sides parallel. And then following from that, there are 4 theorems then that tie in as properties of parallelograms. Opposite sides are congruent, consecutive angles are supplementary, opposite angles are congruent, and the diagonals bisect each other. They share a common midpoint. So we are now armed, everybody, with 5 important pieces of information about parallelograms. 1 was the definition, and 4 of them were properties. So with those 5 ideas in mind, let's start looking at the types of problems we're going to see on our 6.2 homework. And I really hate to say this, but it's good news for you guys. This is another one of those sections where you never need to make an assumption, you guys. There's always enough information presented in the problem that you guys can look at the diagram, assess it, and use the appropriate definition or theorem to solve. However, if you're smart about the way that you make assumptions from a diagram, you guys are probably going to whip through this section very, very quickly and very easily. Let's see what's going on here in problem 3A. Directions are just to solve for x. Let's see what we're dealing with. Without making assumptions, the red arrows in that figure tell me that I'm dealing with a quadrilateral with opposite sides that are parallel. Guys, one thing we normally talk about more in person, but we haven't been able to talk about this here, a cool thing about definitions is that they are reversible. Let me show you what I mean. This definition here on the first slide says that if you're dealing with a parallelogram, then you know it's a quadrilateral with 2 pairs of parallel sides. But since a definition is reversible, you could also read this the other way. If you know that you have a quadrilateral with 2 pairs of parallel sides, then you know that that figure is a parallelogram. Now, as we look at this figure in number 3A, what do we know? Well, we can count the 4 sides in black, everybody, so we know that this figure is a quadrilateral. And from the red arrows, we can deduce or infer that the opposite sides in that parallelogram are parallel to each other. So I can tell from the diagram this is a quadrilateral with opposite sides that are parallel. And because a definition is reversible, we know for a fact now that this figure is a parallelogram. And the 5x plus 15 on the top and the 8x minus 3 on the bottom are opposite sides within a parallelogram. So I go back to my list of properties and I see the one that deals with opposite sides right here as theorem 6.3. Opposite sides in a parallelogram are congruent. And as has been the case all year, congruent means having equal measures. So one of those sides, that's not what I meant to do. I'll go with the 8x plus 3 first, is congruent to or has an equal measure to the top side of 5x plus 15. Again, a lot of you probably knew already that's where we were going just by making an assumption from the diagram. All right, guys, I'm going to combine the x's by moving the smaller one towards the bigger one, so we'll do that. And at the same time, since I moved the variables left, I'll move the constants right by subtracting a 3. I don't really like that super thin pen anymore. We'll do that. Okay, so where are we now, guys? Let's see. Those 3's cancel. Those 5x's cancel. 8x minus 5x leaves us with a 3x. 15 minus 3 is a 12. So now we'll just divide both sides here by 3, and we're going to end up with x is equal to 4. Now the directions simply said solve for x, so we're done, but it's never a bad idea, you guys, to double check your work, and it doesn't take long and it's not hard. If x is 4, 8 times 4 is 32. 32 plus 3 means that this bottom side has a length of 35. That doesn't mean anything to me until I check the top. 5 times 4 is going to be 20, and 20 plus 15 has a length of 35 as well. So now I feel pretty good about my answer because I know from theorem 6.3 opposite sides in a parallelogram are supposed to be congruent, and 35 and 35, yep, those ones are congruent to each other. Okay, so that's a wrap on 3A. Let's move on to 3B. Now again, looking at the diagram, the 4 black line segments tell me that this is a quadrilateral, and the 2 pairs of parallel lines because of the red arrows tells me that this quadrilateral is a parallelogram. Okay, so now what information have we been given in this problem? We've got an angle measure here of 11x minus 4 on the top left, and then another angle in the bottom right of 6x plus 46. So what you guys need to ask yourself right here is, are those two angles consecutive angles, meaning right next to each other, or are they opposite angles, meaning they're on different sides of the figure? And the answer in this case is that those are opposite angles. Top left, bottom right. So I go back to my list of properties and I look for the one that tells me something about opposite angles, and that's the third one here, theorem 6.5, that says opposite angles in a parallelogram are congruent. So what do we know here, guys? We know that the angle in the top left, that's 11x minus 4 degrees, has to be equal in measure to the one in the bottom right, which is 6x plus 46. And again, a pretty easy one to solve. I'm going to subtract a 6x from both sides. So again, variables are all coming left, constants are all going to go right. I'm going to add a 4. Nope. Try that again. I'm going to add a 4 on the left and a 4 on the right to balance that out. 4's on the left cancel, 6x's on the right cancel. 11x minus 6x is 5x, 46 plus 4 is 50, and then quickly we'll divide both sides by 5. And we're going to get x is equal to 10. Now the directions once again just said to do that, solve for x, but it's never a bad idea to check. 11 times 10 is 110, and a 110 minus 4 is a 106 degree angle. How about down here? 6 times 10 is 60, and 60 plus 46 is a 106 degree angle as well. I didn't give you guys another example, and maybe I should have. So let's not change anything that we did here, but just for the sake of argument, what if that 6x plus 46 was actually this angle right here? So don't erase anything that we've done already, guys, but let's just talk about where we're at. If I change the problem now to this, let's go with a lovely shade of pink right here. In this case now, guys, we've got the measure of this top left angle at 11x minus 4, this bottom left angle at 6x plus 46. Now in this case, everybody, we are dealing with consecutive angles right here. So now it would be theorem 6.4 that applies. Those two consecutive angles would be supplementary. And once again, supplementary means adding up to 180. So now we would take the 11x minus 4 and add that to the 6x plus 46, and we would set that sum equal to 180 degrees and solve that equation. Now, I'm not going to go any further because I didn't plan the problem that way, and I think we're about to end up with a really ugly answer because we're going to have a 17x there, and that's not pretty to work with. But I did just want to talk to you guys a little bit about what it might look like if you were given consecutive angles and you wanted to prove that they were supplementary to each other. Okay, that's where we were. And the last problem I wanted to do with you guys is this one right here, example C, and let's see what's going on here. Once again, look at the figure. We've got 4 black line segments, okay, that makes it a quadrilateral, and then the 2 pairs of arrows, the 2 pairs of parallel lines, mean that this is a parallelogram. And what's going on in this figure? If you look at the blue segments that are drawn, we are dealing with diagonals. The diagonals intersect at this point right here in the middle. And if I think about what I know about diagonals, I look at theorem 6.6 right here, which says the diagonals bisect each other. Or, look at it another way, they have a common midpoint. That means that this point right here in the middle, which I'm going to call point M, is the midpoint of each of the 2 diagonals. That tells us that this segment here on the left is congruent to this segment here on the right. And that's the equation that we need, everybody. 5x minus 17 has to be equal to a 3x minus 3. Okay, where are we going from there, guys? We're going to, again, subtract a 3x from both sides, and then also add a 17 at the same time. Those 17s cancel, those 3x's cancel. 5x minus 3x leaves us with a 2x, and a negative 3, careful now, negative 3 plus 17 is a positive 14. and we're going to divide both sides here by 2, and we're going to get x is equal to 7. So there's our answer. Let's check it one more time. Doesn't take long at all. 5 times 7 is 35, and a 35 minus 17 tells us that this piece has a length of 18. How about right here? 3 times 7 is 21, and 21 minus 3 has a length of 18 as well. This is what's supposed to happen in a parallelogram, everybody. That point in the middle, which I've called M, where the two diagonals intersect, that point bisects both diagonals. It's the midpoint of both of them, so it makes total sense that I ended up with an 18 on the bottom left and an 18 on the top right, so I feel pretty good about that answer. All right, guys, that's all the news that's fit to print on section 6.2. So we need to make sure that we know the definition of our parallelogram, and we need to make sure that we know the 4 properties, the 4 theorems that go along with it. Hopefully the 6.2 homework assignment isn't too tough. If you guys have any questions, make an appointment during office hours or ask them in the comments section, and I'll record a video giving you my solution to that problem. Good luck, everybody.